Alright, so our next one is maybe a little more abstracted, but definitely a nice mathy touch to it. The statement reads, two tiny wire loops with areas A1 and A2 are situated a displacement script R apart. We have a diagram for this, so just hold on tight. A, find their mutual inductance. Is your formula consistent with M2 to 1 is equal to M1 to 2? B, suppose that current I1 is flowing in loop 1 and we propose to turn on a current I2 in loop 2. How much work must be done against the mutually induced EMF to keep current I flowing in loop 1? This is going to be a fun question. In light of this result, comment on the interaction energy of the two magnetic dipoles. Alright, so here we go. In our diagram, we have a loop 1 and a loop 2 with vector area 1 and vector area 2 separated by a script R squared. Again, we're going to see some things that we've seen before, except this time it comes together quite nice. Alright, so what we're going to do is treat these loops as dipoles. We've kind of used this tactic before and it worked out pretty well. And if we see that if that's the case, we need the magnetic field of a dipole, which is mu naught over 4 pi, 1 over r cubed, bracket 3 times the dot product of the magnetic moment with the r vector, in the r vector direction minus the magnetic moment. And as you see here, we've seen this before 1,000 times. Now back in chapter 6, we saw what the interaction energy of the two magnetic dipoles was using this magnetic field. So they have pretty similar characteristics here. You just have to multiply or take the negative dot product of M1 and M2 together, and we see that we get this. But let's go back and see how this applies to our current situation. So for part A, the mutual inductance can be found from the flux of B1 through loop 2, i.e. phi2 is equal to M2 to 1 of I1. And so we see that the mutual inductance from 2 to 1 is equal to the flux over current 1. So the flux through loop 2 is take the field from B1 and take the dot product with the vector area 2. And if we do this, again, make sure to use appropriate substitutions. Our separation distance is script R. So our R hats have to be script R hat. And if we take the dot product with A2, we see we get a pretty easy thing to deal with as far as mathematics is concerned. Let's also note that in step 2 of this flux calculation, M1 we know is the magnetic dipole moment, which is just I1 times A1, or the current through the vector area 1. So with that, we're able to plug that in for M1, and what we see is that we have I1 and A1 playing together. Why is this important? Well, we see that we can factor out an I1 now, and we're left with A1 dotted with R hat, which just gives us a scalar, and that points in the R hat direction. And then we have minus A1, vector area 1. So when we take the dot product, we know we can just distribute that in. And we also know that with dot products being commutative, we have that script R hat being able to switch positions with the vector area 2. And we also know that this gives us minus A1 dot A2. So now we're all a scalar, which is wonderful, and that's exactly what we should be. Moving forward, though, if we were to plug this into the mutual inductance, or M21 to find the mutual inductance, we see that we are dividing out the current I, which is pretty much what we expected to do anyways. And then we see that we are in a situation where we have a dot product, and a dot product on the inside of the brackets. Everything else is a nice scalar quantity. And since we know that dot products are commutative, we could switch the order of A1 and A2, and we see that we find that the currents would cancel anyways. So this does indeed hold up that M21 is equal to M12. Again, the physics works. Okay? And then in part B, to find the work, consider the power. We've used this model before, so let's use it again. P is equal to VI. And if that's the case, we know that P, which is equal to dW dt, again, this is from loop 1, is equal to, well, VI is just equal to the EMF. Again, that's going to be negative. And then I1, okay, because it has to, the mutual inductance has to be negative to restore it. And then if we take the integral with respect to time, we see that we get the negative E1 I1. And what this means is that this is the work done per unit time against the mutual EMF in loop 1, hence the minus sign, against the mutual EMF. So we want it, again, let's go back to the question. We want to keep the current running against this mutual EMF. And that's why we have to have the minus sign. All right. But we also know that the EMF is equal to the negative time derivative of the flux through, or flux 1. And so we know that that's equal to, well, if flux is equal to MI of the second current, we'll just plug that in and we see that we have the EMF is equal to negative M, the mutual inductance, times di squared dt, okay, all fair substitutions. And if we plug that in, we see we get a lot of negative signs, so be careful. The negative signs cancel in the integral. And we also see that we have dt's canceling. Okay, although mathematically that's not accurate to do. We're all playing physics here, just getting rid of things that we can. What we see is that with this, I1 is constant and I2 is the final current in loop 2. And so with I1 being constant, we can move it out the integral. And then the di2 undoes itself with the integral. And we're left with work is equal to the mutual inductance times both of the currents. Okay, that's easy to deal with. We already found what the mutual inductance was. Now just multiply by both of the currents. And we see that if that's the case, we can split up I1 with A1 and I2 with A2 in both respective cases. And lo and behold, what do we get but the magnetic dipole moment again? Wonderful how consistent this is, isn't it? There is a more lengthy discussion that I'll post in the comment or the description. But here's at least how you can walk through this. Again, it's not too hard. We just have a couple things to maneuver. Dot products again are your friend. But you see how it's easy to cancel things or reassemble things piece by piece when you take it step by step. Pretty cool.